Ela bate, 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 bate.
Assalamualaikum and good morning. Today we are from Group 2. We'll be presenting our mini project for ECW 437, determination of coefficient for discharge for two different sharp edges orifices. Orifices are commonly used in hydraulic structures such as reservoir, irrigation system, water treatment plants, and stormwater drainage facilities to regulate and measure flow. However, the actual discharge through an orifice is always lower than theoretical discharge due to energy losses, jet contraction, and fluid friction. Therefore, this experiment aims to determine the coefficient of discharge, compare the discharge characteristic of two different orifice diameter, and evaluate the influence of orifice size on flow behavior.
Drainage system and culvert are designed to safely convey stormwater and prevent flooding. Their performance depends on an accurate coefficient of discharge, which determines the actual rate through an orifice. If this value is inaccurate, the outlet may be undersized, causing flooding or oversized, which can lead to downstream erosion. Therefore, determining the coefficient of discharge is essential for designing safe, efficient, and reliable stormwater drainage system.
The experiment is based on the principle of continuity and Bernoulli's equation. When water flows through the end orifice, the stream contracts immediately after leaving the opening, forming a region known as the vena contracta. Due to this contraction and energy losses, the actual discharge differs from the theoretical value. The theoretical discharge is calculated using Qt is equal to A square root 2gh, where A is the area of the orifice, g is the gravitational acceleration, and h is the water head. The actual discharge is determined experimentally by measuring the volume collected over a specific period. QA is equal to Vt. The coefficient of discharge is then calculated using CD is equal to QA over Qt. This coefficient combines the effect of contraction and velocity losses and represent the efficiency of the orifice. The experiment was designed by varying only the orifice diameter while maintaining consistent operating conditions. The independent variable was the orifice diameter, which is 0.004 meter and 0.008 meter, while dependent variable was the discharge rate. Control variable included water temperature, tank geometry, measuring method, and head measurement procedure. This design ensured that any variation in discharge was primarily due to changes in orifice size.
Firstly, we measure the diameter of the orifice using a vernier caliper.
And then, we place a paper on board and secure it using the magnet.
And then, we install the orifice with a size of 0.008 meter to the orifice tank. Then, close the outlet valve and fill up the tank with water.
Adjust the water level to the required head above the orifice. We must make sure that the water head is stable and constant before we taking any measurement.
Next, we measure the head using ruler, which is 0.25 meter. The point gauge to the top of water flow and mark the height on the paper.
Next, collect the discharge water 0.5 meter using a beaker and record the time using a stopwatch.
Lastly, repeat step 1 to 9 using another orifice with a size of 0.00.
For each experimental run, the actual discharge was calculated using the measured volume and collection time. The theoretical discharge was calculated using the orifice equation based on the measured head and orifice area. The coefficient of discharge was then obtained by dividing actual discharge by theoretical discharge. For example, for orifice A, the measured discharge produced a coefficient of discharge which is 0.808 and 0.770. Similar for orifice B, the coefficient of discharge is 0.844 and 0.811. The results show that the larger diameter produced a higher discharge due to the larger flow area. The calculated coefficient of discharge were found to be within the expected range reported in hydraulic engineering literature, indicating good agreement between theory and experiment.
For discussion of result, the experimental result demonstrate that distance increases with increasing orifice diameter to the larger cross-sectional flow area. Although the theoretical equation predict the maximum possible discharge, actual discharge remain lower because of friction, losses and vena contracta effect. The coefficient of discharge obtained from the experiment reflect these hydraulic losses and provides a correction factor for engineering calculation. These findings are important for the design of hydraulic structure where accurate flow prediction is necessary to ensure safe and efficient water management. The study also supports sustainable development goal 9 by contributing to the improvement of structure-related engineering applications.
In conclusion, the experiment successfully achieved all its objectives by measuring the actual discharge, calculating the theoretical discharge using Bernoulli's and Terreslis theorem, and determining the coefficient of discharge of the orifice. The results show that the coefficient of discharge is crucial in representing real flow condition, as actual fluid flow is influenced by the energy losses. By applying the experimentally determined coefficient, engineers can design more accurate culvert and drainage outlet structure, leading to improved stormwater management, reduced risk of flooding and erosion, and the development of safer, more sustainable hydraulic infrastructure in support of SDG 9, industry innovation and infrastructure. That's all from us. Thank you.